This is the reality of seismic pressure, a concrete structure forced into a state of violent, unpredictable vibration. To engineer against this, we have to predict exactly how the material will move before the first tremor hits. Physicists govern these interactions using the wave equation, expressed as Lu equals F. It is the core mathematical law for any system where energy moves through a medium. In this relationship, L represents the differential operator, the physical properties of the structure itself. F is the external force, like the earthquake, and U is the displacement, the actual movement we need to calculate. While this equation is elegant, it is only a definition of the system's requirements. Stating the equation is simply identifying the relationship. It doesn't provide the specific numerical values for how the structure is actually bending at any given second. The central paradox is that the wave equation tells us how displacement must behave, but it cannot directly output a specific numerical answer for a complex scenario. This occurs because real-world forces are rarely a single, clean pulse. They are continuous, messy, and constantly mutating over time. When you account for shifting points of impact, unique starting positions, and fluctuating boundaries, the math becomes a recursive loop. Every new second of force changes the starting conditions for the next. Attempting to solve the wave equation analytically from the ground up for every unique physical event is prohibitively slow and inefficient. The equation functions as the problem statement, requiring a more specialized tool to produce a functional solution. To build that tool, we simplify. We strip away the earthquake and look at a single pristine steel beam. We watch what happens when a single concentrated point of force strikes the center. This is a unit impulse. We are applying exactly 1 unit of force at one precise point for a single infinitesimal moment in time. The resulting response is Green's function, the exact mathematical map of how this system reacts to that singular tap. By solving this isolated event, we create a standardized mathematical component, knowing the fundamental reaction to any impulse, anywhere, at any time. By isolating this single spark of energy, we create a reference point that allows us to describe the behavior of the entire structure. Now, we reintroduce the messy, continuous forces of the real world. We apply superposition. Any continuous force is the sum of millions of tiny point inputs. We deconstruct the earthquake into individual taps. For each tap, we scale our Green summation to match. Finally, we integrate, summing these scaled responses to reveal the structure's exact final displacement. We have shifted the task from solving an inefficient equation to assembling known responses. We are mathematically reconstructing the complex reality from simple, pre-verified parts. This highlights the functional difference between the two concepts. The wave equation is the law the system must obey. Green's function is the modular response that makes calculating that obedience possible. Solving for the unit impulse provides the necessary bridge to handle general forces, turning an abstract differential equation into a solvable integral. This framework is used far beyond civil engineering. It is how we model the way light moves through fiber optic cables, how heat dissipates through a computer processor, and how electrons behave in quantum fields. In each of these fields, the complexity arises from the same source, thousands of overlapping interactions occurring simultaneously across a medium. The power of Green's function lies in its scalability. By defining the consequence of a single, isolated impulse, we can accurately predict the behavior of any linear system, no matter how many millions of inputs are acting upon it at once.